In this video, I'm going to show you how to use a validation set to stop the training of a neural network exactly at the point where it converges and before it overfits. We're also going to talk about improving the performance of your neural network and getting that last squeeze of enhanced performance out of your dataset. So let's get started. Overfitting is a very common problem that we face when we train machine learning models or neural network. We can visualize overfitting by looking at the difference between our training performance and our test performance. The moment that we see that our training performance is much better than our test performance and that our neural network is achieving much better accuracy or lower loss on our training set, and that's basically not happening on our test set, then our neural network is simply not generalizing well to unseen data, and this is basically the definition of overfitting. We've seen in a previous video how to build and train a neural network, and the first step into preventing overfitting is to build a validation set. You can simply build a validation set by defining a validation split parameter over here, giving it a fraction of how much of your training data should be used for validation. Now, in our history parameter that we will get back here from the fit function, we will have the value of the validation set loss and any other metric that we've defined, like the accuracy, for example, or the mean absolute error in our case. We will have the value of the loss and the metric on our validation and on our training for both sets, the training and the validation, through each epoch. If we plot this information, it will look something like this. We will be able to see the difference between our network performance on the validation and the training. And we can see clearly, for example, that over 200 epochs, our neural network has improved, but it was mostly on the training set. And that's a clear sign of overfitting. To prevent overfitting, we have to call our good friend early stopping. Early stopping is a keras callback that will be used during our training to stop the training exactly when our validation does not improve anymore. However, you shouldn't do that on the first time that this happens. You should let the neural network try a couple of times to improve the performance, and that means defining a Bayesian. It's the number of epochs that a neural network is allowed to continue training before early stopping will stop the training. Another very important parameter over here is the restore best weights, which will reverse our weights in the neural network to the point before it started overfitting. So this allows you to give a much higher Bayesian, like 20 or maybe 50 epochs. And even though you've continued to train the neural network for, let's say, 50 epochs, you will still go back to the point before the overfitting started, which is perfect. So we can define the early stopping over here. We can define which value you would like to monitor. The validation loss is a good monitor for the early stopping to keep an eye on. We can define a Bayesian of any value depending on how big your neural network and how many data points you've got. And always remember to restore the best weights. You can pass the early stopping as a callback over here to the fit function. It takes a list, so make sure to put it in that list. So now when we train our neural network with early stopping, we will be able to see at which epoch it stopped. For example, here it stopped at epoch 22. However, the best weights were at epoch 12. So if you look over here at our plot, we can see that around epoch 12, the validation loss was at a minimum point. Further on, the loss has enhanced on the training, but that wasn't the case for the validation. And that's a clear sign of overfitting that we've managed to stop thanks to early stopping. Now that we've stopped overfitting as much as possible, we can look at the other end of our neural network, which is improving the performance. The performance can be improved a bit further just to squeeze the best out of your data by using the reduced learning rate on plateau. When we use an optimizer, our optimizer will have a learning rate, and that will decide how big of a jump it will take on the loss plane. In many cases, this learning rate will be a bit too big to find the perfect minimum in that loss. As you can see over here, our optimizer could be stuck jumping around. However, it will eventually hit a very close point to the lowest loss. And we can speed up that operation by reducing the learning rate, by making it take even smaller steps until it finds that perfect minimum loss. To find the bottom of the loss function, we can use the reduced learning on plateau, which will basically make our steps smaller when our loss does not enhance anymore. It takes a Bayesian, just like the early stopping, which defines how many steps it should take before it makes the learning rate smaller. And it takes a factor, which is a multiplier that will be multiplied by our learning rate. So in this case, we are decreasing our learning rate by 1%. So in our previous neural network, before using the reduced learning rate, we've managed to hit around 94%. However, now we're managing to get a bit higher value. We're hitting around 95% accuracy, which is pretty awesome. That was everything I wanted to talk about for today. I hope you enjoyed this video, and I hope it will make your neural network better. Until next time.